Hello. So we're going to talk about ionic bonding today. Ionic bonding occurs between metals and nonmetals. So as you remember, metals tend to lose electrons when they bond. Nonmetals tend to gain electrons when they bond. So they give and take electrons to each other. So ionic bonding occurs between metal cations and nonmetal anions. The ionic bond itself, we talked about it being the attraction, remember the electrostatic or Coulombic attraction between the positive cations and the negative anions. So we're going to say the electrostatic force or attraction. In chemistry, force means attraction, or Coulombic attraction, whichever you prefer. And all that means is positive negative attraction between positive and negative ions. Okay, so we're going to use a variety of different things. We're going to use Lewis dot structures. We're also going to use electron configurations to show how metals and nonmetals bond together. So just a quick review of Lewis dot structures. Lewis dot structures are used to represent valence electrons. And the maximum number of valence electrons, as we saw from last chapter, is 8 valence electrons, right? The S's and the P's would be your valence sublevels. So when you draw Lewis dot structures, basically you put, it doesn't matter where you start, which side you start on, but whatever side you start on, you put 2 electrons next to each other first. So I'm going to say the first and the second electron go here. I'm using numbers to show you the order, but you would use like little dots to represent the electrons. And the reason why we put these together is those are the electrons that go in the S sublevel. And then the other 3 sides represent the P sublevel. And so when we fill them in, we go 3, 4, 5 before we pair them up, 6, 7, 8. Again, it doesn't matter what the order is. What matters is the first 2 electrons are always next to each other, and then the other 6, you put 1 in each side first before you go back and pair them up. Just like the S sublevels fill up first, and then the P sublevel fills up next with 1 electron in each orbital first. So let's look at sodium chloride. So sodium's Lewis dot structure would be Na with just 1 valence electron. The electron configuration for sodium, for just neutral sodium, would be 1s2, 2s2, 2p6, 3s1. For chlorine, chlorine has 7 valence electrons, so there's 1, 2, 3, 4, 5, 6, 7. And its electron configuration, I'm going to use the noble gas shortcuts. So I'm going to use neon, then 3s2, 3p5, 3s2. All right, so what happens when sodium and chlorine bond together is that the sodium, because it has 1 valence electron here, it wants to get rid of it, whether you're looking at this or this right here, it wants to get rid of this electron so that it would have a noble gas configuration like neon. The chlorine has 7 valence electrons. It would like to gain 1 to put it here, or to put it in the 3p there, to make it full like argon, right? So what happens is, I'm going to use a different color here. The sodium takes that electron and gives it away, and the chlorine takes that electron. Same thing with the electron configuration. This electron is given away to the chlorine. So what results is sodium ion without that extra electron. So when we show the Lewis dot structure, we show sodium. Normally it has 1 valence electron, but it loses that valence electron, so now we don't show it with anything, but to show that it's an ion, we put brackets around it and the charge. For the electron configuration, this was neutral sodium. When it loses that electron, it becomes 1s2, 2s2, 2p6. Isoelectronic. Iso means the same, electronic means electrons. This has the same electron configuration as what? What has an electron configuration of 1s2, 2s2, 2p6? Well, that is neon. And that's exactly why sodium bonds, and it gives away that electron to become like neon. Okay, let's look at the chlorine. So the chlorine gained an electron to become chloride ion. So normally it has 7 valence electrons, but now it gained one more. So we need to show that. So there's 1, 2, 3, 4, 5, 6, 7. Those are the normal 7, but then it gained one more, so we're going to put it here. And to show that it's an ion, we always put brackets and the charge. Let's look at the electron configuration. So this is the electron configuration of neutral chlorine, 3s2, 3p5. We're going to gain one more to make it 3p6. So then the new configuration is neon, 3s2, 3p6. Well, what is that isoelectronic to? This is the electron configuration of argon. So that makes the chloride stable. Chlorine, neutral chlorine is not stable. Neutral sodium is not stable, but sodium ion and chloride ion are stable. That's why sodium is very dangerous, chlorine gas is very dangerous, but we eat sodium chloride and we're totally fine. Okay, so to show this, we're going to write the formula. The formula would be NaCl. Oh, sorry, it's already there. I don't need to write it here. There is the formula down there. Here it is. And this chemical formula is telling us we take one sodium, one chlorine, put them together. Now, even though it's made up of ions, in the formula we never show the charges because the compound has to be overall neutral. So 1 plus 1 minus makes it neutral, so we don't put charges here. To show the formula with the Lewis dot structures, we basically put the two ions next to each other like this. Okay, let's look at a different one. Calcium fluoride. So calcium has 2 valence electrons, so it looks like this. And the electron configuration for calcium is argon. Well, let's actually write it out. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. For fluorine, fluorine has 7 valence electrons. 6, 7. And its electron configuration is 1s2, 2s2, 2p5. Okay. When calcium bonds, it becomes calcium ion, so Ca2+. So it originally had these 2 valence electrons, but then Ca2+, you lose those 2 valence electrons, so you write it without any extra electrons on it, and you put brackets because it's an ion, you write the charge. For the electron configuration, it loses these electrons to give to the fluorine. So it becomes 1s2, 2s2, 2p6, 3s2, 3p6, which is isoelectronic to argon. For the fluorine, fluorine, when it bonds ionically, it becomes F-. That means it gained 1 electron. So it originally has 7, so it gains 1 more. That minus means it gained 1 more. So here are the original 7. We're going to add 1 more because of that negative charge, and we put brackets around it to show that negative charge. And for the electron configuration, originally it was 1s2, 2s2, 2p5, so that negative means it gains 1 more. So it becomes 1s2, 2s2, 2p6, which is isoelectronic to neon. Now, notice that the calcium gave away 2 electrons, right, to become Ca2+. The fluorine only gained one of those electrons. So where did the other electron go, right? One of these went to the fluorine. Where does the other one go? Well, it goes to another fluorine. So actually, in order for calcium and fluorine to bond together, you need 1 calcium and 2 fluoride ions. How do we know that? Well, when we write the charges, we can look at the charges, and we need to be able to make a neutral compound. If we were to put 1 calcium ion with 1 fluoride ion, the total charge would not be neutral. Let's do it. So if you have a Ca with a 2 plus and then an F minus like this, well, that's not neutral. That adds up to +1. It needs to be neutral for the compound to exist. So what happens is another fluorine reacts. And so I'm going to write another fluoride here. And now we have 2 negatives, 2 positives. That is neutral, so that can exist. So the chemical formula is CaF2. When you write your chemical formula, you always write the one that is positive first, like the metal first, and then the nonmetal comes next. So the positive first and then the negative. So CaF2, which is calcium fluoride. Let's try to practice one more. Aluminum oxide. So aluminum is Al with 3 valence electrons, and its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. Oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. And its electron configuration is 1s2, 2s2, 2p4. So what's going to happen is the aluminum is going to get rid of these 3 electrons, these 3 right here, or those 3 right here, and it's going to become Al3+. So since it had 3 electrons and now it lost 3 based on that 3+, now we don't show any next to it, and we write 3+. For the electron configuration, it becomes 1s2, 2s2, 2p6, which is isoelectronic 2 neon. Let's look at the oxygen. So the oxygen had 6 valence electrons, 1, 2, 3, 4, 5, 6. And that -2 tells us that it gained 2 more. And so we need to add 2 more. So there's 1, there's another one, and we put brackets around it in the charge. For the electron configuration, here's the neutral oxygen. It gains 2 more. So instead of 2p4, it becomes 2p6. So 1s2, 2s2, 2p6, also isoelectronic to neon. So let's try to put it together to form aluminum oxide. So what do? Well, we take one of the aluminums and we take one of the oxides, one of each to start with. And we check, is this neutral? No, it's not. It adds up to +1. That's not neutral, that can't exist. So since it's positive, we need to add 1 more of whatever is negative, right? So let's add another oxide. And now let's check. Oh, that's still not neutral. That's -4, +3, so that adds up to -1. That's not good. That can't exist. So since it's negative, add 1 more of the positive. So let's add another Al3+. And check. Well, still not neutral. We have +6 and -4. That adds up to +2. So since it's positive, add 1 more of the negative. You keep going until you make it neutral. So add 1 more of the oxide. Let's see. Now there's +6 and -6. That is neutral. So that is correct. the chemical formula would be, we need 2 of the aluminums and 3 of the oxides, so Al2O3. So I do want to review with you, though, the charges on the periodic table. So let's go to a periodic table and check. We've reviewed this before, but I want to make sure that you know it. So group 1 is always +1. Group 2 is always +2. Don't worry about the transitions for now. The boron family is +3. Carbon family is ±4. Nitrogen family is -3. Oxygen family is -2. Halogen family is -1. And then these don't get a charge. So again, to review, +1, +2, skip, +3, ±4, -3, -2, -1. So if you are given aluminum and oxygen and you're not given what the charges should be, you should still be able to figure out what charges they would become. All right, so if you were in class, we would use ionic models to build ionic compounds. So let me show you what that means. So you would be given these right here. They'd be printed out. And let's say you want to make potassium chloride. So you take a potassium, which is right here. Potassium is a +1 charge because it's a group 1. You take a chloride, which is -1 because it's a halogen, and you make 1 formula unit of potassium chloride. You write the formula, then it would be KCl. And then you draw a particle diagram, a picture of what this looks like. So let's try another one. Let's try let's try lithium and oxygen. So lithium is +1, so you draw a circle with a +1. And oxygen is -2, so you draw a circle with, you can put 2 negatives like I have here, or you can just write 2 minus and check. Oh, this is not neutral. This doesn't look right. Right? This is a +1 and a -2 for a total of -1. So what can I do to make it neutral? Well, I'd need another lithium. So grab another lithium. And now 2 pluses, 2 minuses, that is neutral. So that is the particle diagram is what we're going to call it. And it would be Li2O for the formula. So let's go back here. So to draw the particle diagram, basically you do a circle, put the symbol in the charge like this. That's called a particle diagram. The formula would be KCl for this one. For the next one, Li with a plus, O with a 2 minus, and then another Li plus, and then Li2O would be the formula. So I want you to pause this video and practice these and see if you can draw the particle diagrams and also write the formula. You can be asked to do both on the test. So pause this video and then play it again when you're ready and check your answers. All right, so hopefully you're back and you did these. Here are the answers. So this one you would need 1 of the aluminum ions and 3 fluoride ions, so AlF3. For this one you need just 1 of each because it's +2 and -2, so MgS. For this one you'd need 3 calciums and 2 nitrides, so Ca3N2. And for this one you need 4 of the cesium ions and 1 of the carbide ions, and so CS4C. All right. Let's look at polyatomic ions. So when we studied ions, we talked about anions and cations. There is something called polyatomic ions. Let's look at what that means. So poly means many. Atomic obviously means atoms, so many atoms. Ion means it has a charge. It has lost or gained some electrons, so it has a charge. So this means you have many atoms with an overall charge. Many atoms that have collectively either lost or gained some electrons. So many atoms with and overall charge. There are many, many, many polyatomic ions, like hundreds of polyatomic ions. These 12 are the most common 12 that we're going to be using this year, and I would like you to memorize them, and we're going to have a quiz over those. So for the quiz, I will either give you the name, you give me the formula, or I'll give you the formula, give me the name. For the name, spelling counts. For the formula, the capitalization counts, the superscripts and the subscripts count as well. Now, after that quiz, you will be able to use your periodic table on the test, and on the back of the periodic table, you will find that, so here's the periodic table that we use for the test. On the back, you will find many, many polyatomic ions, a lot more than what these are. And on the test, you are able to use this, so you don't need to memorize them anymore. So you just need to know them for the quiz, and then after that, you just need to be able to use them. They are there for you on the periodic table on your reference sheet. So what does it mean? Well, for example, ammonium, NH4+, that means you have a nitrogen bonded to 4 hydrogens, and overall, all 5 atoms together have lost 1 electron to get a +1 charge. So most polyatomic ions, actually all the ones that I know of, except for ammonium, are all negatively charged. Ammonium is the only one that is positively charged that I know of. All of the other ones are negatively charged. You'll notice that a lot of them have similar names, like there is nitrate and nitrite, sulfate and sulfite. Usually the ones that ends with ate have 1 more oxygen than the ones that end with ite. So nitrite is NO2 minus, nitrate is NO3 minus. Sulfite is SO3 minus, sulfate is SO4 minus. So the ate always has 1 more oxygen than the ite. So hopefully that kind of helps you study for them. So these are ions still, so they can ionically bond, right? So let's practice doing some of these. If I have sodium ion and I want to react it with a nitrate ion, combine it together to make sodium nitrate, what does it look like? So what you do is you take a sodium ion. Let's draw the particle diagrams for this. So sodium is Na plus because it's in group 1. Nitrate, if you look at the list that we have here, here is nitrate. It's NO3 minus. Check that it's neutral. And remember that that 3 as a subscript means there's 3 oxygens. The charge is just -1. So watch out that you're looking at the charges that are the superscripts, not at these numbers here. So this is a +1 ion. This is a -1 ion. That is neutral. So that's it. So I write my formula as NaNO3, just 1 of each. 1 sodium, 1 nitrate ion. Let's look at the next one. Calcium ion and nitrite ion. So calcium ion is Ca with a 2+ because it's in group 2. Nitrite is right here. So NO2 with a minus. Now, is this neutral? It is not. We have a +2 and we have a -1. So what do? We need another nitrite. So draw another nitrite, NO2 with a minus. And now we have 2 minuses. We have 2 pluses, so that is neutral. So how do we write this? So you write your metal first, whatever's positive first, right? So calcium, we only need 1 of those. And then the nitrite is NO2, but we need 2 of those. Now, what happens if I put a 2 here? Well, that doesn't look like the picture I drew, right? This looks like a nitrogen with 22 oxygens, when in reality, it's 2 of the NO2s, right? So what you do when you have a polyatomic ion and you need more than 1 of them, you put parentheses around it. So this means 1 calcium and then 2 of whatever is in the parentheses, so 2 of the nitrites. Let's try barium hydroxide. Barium is in group 2. So it looks like this. Hydroxide is OH minus right here. Is this neutral? No, it's not. I have +2 and a -1, so I need 1 more of the negative ion another hydroxide. Now it's neutral, 2 pluses, 2 minuses. So I write Ba, I just need one of those, and then OH. And again, if I put a 2 there, that looks like I have 1 oxygen and 2 hydrogens. That's not the case. I have 2 of my hydroxides, so I put parentheses around my OH because I'm doubling the whole thing. Let's do letter L, ammonium ion and bromide ion. So ammonium is NH4 plus. Bromide is Br with a minus because it's in group 17, it's a halogen. So plus 1 minus 1, that's neutral, so the formula is NH4Br. One of each. Let's do one more. How about strontium ion and phosphate ion? Let's do that. Strontium is Sr2 plus. Phosphate, that's a polyatomic ion. And it is right here, it's PO4 3 minus. So you write that. PO4 3 minus. Is that neutral? No, it's not. 2 plus and 3 minus, that adds up to -1. And so I need another one of the strontiums. Is that neutral? Not really. I'm +4 and -3, so add one more of the phosphates. Is that neutral? No, it's -6 and +4. Add one more of the strontiums. And now you've got +6, -6. So you're going to write Sr, there's 3 of those, and then PO4, and there are 2 of those. So that is the chemical formula for it. So I want you to pause this video, practice the other ones, and then come back and play the rest of the video so you can see the answers. All right, so hopefully you're back. Check your work. Make sure that you got them all correct and that they are all neutral. The formula is correct, and then also the particle diagrams are correct. Remember, the particle diagrams, you need to show your ions, your charges, but in the formula, you never put the charges in there. Now, it might have been a little challenging trying to figure out, like this one. That's just nitrogen, right? It's hard to tell what is nitrogen, like N3 minus versus NO3 minus versus NO2 minus, so which one's which? So here's a little clue. If it ends with ate or ite, then it's definitely a polyatomic ion, and you get it from the back of the periodic table. So nitrate, ate, nitrite, those are definitely polyatomic ions. If it ends with ide, IDE, like nitride, most likely it's going to be a monoatomic ion. It's going to be from the regular periodic table, like nitrogen. So again, if it's ate or ite, it's a polyatomic ion from the back. If it's ide, then it's from the front of the periodic table, it's monoatomic. There are a couple of tricky ones that are polyatomic ions, but they end with ide, so you have to be careful. The 2 that you need to know about, that you need to memorize, are cyanide and hydroxide. Those end with ide, and yet they are polyatomic ions. There are a couple of other ones like azide, a few more, but those are the most common ones that end with ide, but yet they are polyatomic ions. So ite or ate, you look at the back. Ide, for the most part, you look at the front of the periodic table. I want to show you one more trick for how to come up with the chemical formulas without drawing these particle diagrams and figuring out like how many of each. It's called, well, I guess it's not really called anything, but you crisscross and you reduce. Crisscross and reduce is what I personally call it. So what that means is, let's say we are doing this one here. So what you do, or let's do calcium ion and nitrite ion. So what you do is you write your ions and you crisscross the charges, put them as subscripts, but for opposite. So the 2 plus from the calcium goes with the nitrite, The one from the nitrite goes with the calcium. So you get 1 calcium and 2 nitrites. See how it's 1 calcium and 2 nitrites? How about this one, strontium and phosphate? So strontium is R2 plus, phosphate is PO4 3 minus, so switch them. So this becomes a 3 and this becomes a 2. So SR3, PO4 2. You have to be careful though, when you do this method, that you have to reduce. For example, let's say you have magnesium ion and sulfite ion like this one, Mg2 plus and SO3 2 minus. Well, if you crisscross, you'd get 2 and 2. You got to realize that that reduces to 1 and 1. If you write this as Mg2 SO3 2, then that would be wrong. So you crisscross, but then you also reduce. This works for polyatomic ions and non-polyatomic ions. So if you do it for this one, Be2 plus and 3 minus. So you crisscross. So this becomes a 3, this becomes a 2. So Be3 and 2. Hopefully that helps. See you guys.